Welcome to the HyperX Academy. Today's tutorial is going to cover a case study involving the Collier Aerospace UAM wing model. The objective of this case study is to use HyperXpert, our new design of experiments tool, to optimize the upper skin for both weight and manufacturability. HyperXpert provides all positive margin designs resulting from a full factorial design of experiments and a platform to compare the solutions yourself. It allows the user to decide which design works best for their situation. First, let's review the sizing setup. It has 8 total variables, 6 geometric variables for dimensions, and 2 variables for the skin and stiffener material. Notice we are manually setting 4 of the variables from the design property to be unable to vary, thereby ensuring they are the same across all panels linking them. This leaves the remaining 4 unlinked, meaning not a set constant value is required for all panels. As you can see from the Analysis Property window, we will begin this analysis using panel buckling, stiffener buckling, local buckling, crippling, metal strength, and stiffener skin bonded strength failure modes. To introduce this capability, we'll be sizing the upper cover of the UAM wing as metal T-stiffened panels. To demonstrate the benefits of the HyperXpert results, let's first get a baseline using the HyperX sizing algorithm, and then compare them to the HyperXpert results later on in the case study. By design, the HyperX algorithm found the lightest weight design of 102.7 pounds while attaining positive margins of safety for each panel. However, because HyperX is sizing on a per-panel basis rather than a per-part basis, the resulting design can look radically different from zone to zone. And this increased variation in design across the upper skin part surfaces makes it difficult to manufacture. Prior to HyperXpert, this is something you would attempt to fix manually by using engineering intuition to manually select variables to link at particular values and size each individual combination, thereby running a trial and error process. Or, use a script to vary each unlinked variable at particular values, run a sizing, and then pulling out the lightest weight, essentially an automated but still a trial and error process. In either case, there's no way to guarantee you've selected the right combination of linked variables will result in the lightest weight but also a manufacturable design. Or, you could run a design of experiments that systematically evaluates the full factorial combination of all designs in the experiment space across the entire part. To set up a run set and run HyperXpert, let's first open the HyperXpert Run Set Definition form located on the Run tab of the ribbon. Then, select the upper skin part as HyperXpert solutions will be part-based, not zone-based. Notice the form automatically populates with the setup information corresponding to the selected structure. Next, click Run to initiate the design of experiments. HyperXpert is now running a full factorial design of experiments of all possible linked variable combinations. This process will take a bit longer than your traditional HyperX sizing run. Now, let's open the HyperXpert viewer and review interface to review the results. To do so, open up the HyperX viewer from the Run tab of the ribbon. Then, use the green plus sign to open the run set library and select the run you just generated. Each data point on the plot corresponds to a part design that attains all positive margins of safety. In our case, each data point represents a particular design for the upper skin of our wing. These data points are plotted in terms of part weight versus number of unlinked variables. The anchor point, the point furthest to the right, represents the optimum solution that HyperX proper provides and can be helpful for providing context. In general, you'll notice that the designs that are the easiest to manufacture are heavier than dimensionally optimized parts that inherently add manufacturing complexity. The tree on the left-hand side of the plot is used to show and hide data as well as to identify particular data points based on linked variable dimensions. By default, all parts start as unidentified until particular tree nodes are selected. The legend is used to interpret identified data points. It can also be used to show and hide particular selections of data based on their identification. Clicking on individual points will automatically add that point and its corresponding metadata to both the point information pane and as a row in the point grid. These tools are used to better understand the designs characterized by each data point of interest. The Pareto frontier, which is automatically plotted, helps to identify the most optimum solutions. The points along this curve are the Pareto optimum points. As we can see, the best solutions minimize the number of unlinked variables and minimize weight. When comparing the bookends, the point furthest left and the anchor point, we will notice the most manufacturable solution is over 70 pounds heavier than the HyperX optimum solution, but has a constant design over the entire skin. We can use the tree to identify points by the linked dimensions as well. If we expand the panel section of the tree, we can see for each cross-sectional variable, each possible dimension in the design space is a node on the tree. Clicking the circle corresponding to a particular value will identify all solutions that are linked at that value. For example, if we click on the spacing equals 2 inches, the red series that is indicated on the legend represents all of the solutions where the part has a consistent 2-inch spacing between stiffeners across all zones. The filled teal circle indicates the dimensions that are identified, and the legend identifies which series is which. If we click on one of the spacing dimensions a second time, it will hide all solutions associated with that value. By eyeballing the Pareto frontiers for each series, we can see that a stiffener spacing of 2.8 inches seems to generate lighter optimum solutions. Now, thinking like an engineer, stiffener spacing is the most advantageous variable to link in terms of manufacturability. So, let's leave the 2.8-inch values identified and double-click on the 2-inch circle to unidentify but still show the other points. Another linked criterion we might want to consider based on our manufacturing process is stiffener height. So let's identify solutions based on stiffener height values as well. Notice that selecting heights adds 3 more series to the plot, as well as an additional over-identified series. This indicates that there are points that are linked by more than one of the selected dimensions. To better understand, let's click the Color Over-Identified option. The over-identified series has now become identified by multiple variables. By comparing the Pareto frontiers, we can see that the dark green curve is the optimum solution. This design has a linked stiffener spacing and stiffener height, increasing the manufacturability of this part. Additionally, because the thickness of the skin and the stiffeners are allowed to vary as needed depending on the load path, this solution is a fairly reasonable weight. This weight is only 4 pounds more than the HyperX solution at the anchor point. So, for a cost of only 4 pounds, we can drastically increase manufacturability. Another way to get this same solution would be using the point grid. By proceeding from right to left along the Pareto curve and selecting each point along the way, we can build a table that compares the lightest weight solutions at each x-axis value. Being able to directly compare these weights side by side allows us to make an educated decision on which design to select. Using the same logic as before, we would pick this point as it links my 2 priority variables and is the lightest solution that does so. We can also see that after this point, linking additional variables becomes a lot more costly in terms of part weight. Now that we've identified our preferred design, click the Create Design Property option either in the point grid or the point info window. This will automatically create a design property corresponding to the design we selected with constant inputs for the variables that are linked. Notice that the stiffener spacing and height variables are forced to be constant at the dimensions we identified. Now, let's select the upper skin and click Assign to assign this property. Now that the new design property has been assigned, let's do another sizing run and see the final result. Notice the total weight is the exact same as what we saw for HyperXpert, and that we maintained all positive margins of safety. Also, notice that when we check various design results, we see a constant 2.8-inch spacing, rather than the varying spacing across the panel we saw with the prior design. And that wraps up our case study using HyperXpert. HyperXpert is an extension of HyperX and provides all data from a full factorial design of experiments and a platform to compare the solutions yourself. It allows the user to decide the best design for you, knowing you did your due diligence looking at all possible options and trends. Thanks for stopping by the HyperX Academy.